Hi guys, this is the third in our series on probability distributions for continuous random variables. So number 3, in part 1 we looked at probability distributions for continuous random variables in general. In part 2 I went specifically into normal distributions using the empirical rule. And here in part 3 I want to talk about uniform probability distributions. Now I chose these, first the normal distribution using the empirical rule, and then uniform probability distributions, not only because they're so commonly included together in statistics textbooks, but also because we can work with these without any sort of calculus, and in fact just like the most basic algebra, and we're going to be able to do some good work with these probability distributions and make them work for us, do some functional work with them. So what is a uniform probability distribution? Well, unlike a normal distribution, which is a bell curve, it's peaked in the middle and it dwindles at the edges, a uniform probability distribution is characterized by having a top which is just a straight line. In regular math, in algebra, we would say that it's a linear function with a slope of 0. In probability and statistics, we call it a uniform probability distribution. So in profile, it looks like a warehouse from the side in silhouette. It's a flat-topped construction of constant height. And that's actually what makes it easier for us to work with. Let me give you some examples. Let's say that I have something that I'm studying, the arrival time of the next train on the train station, or could be anything else, that has an equal probability of occurring, either the train arriving or any other phenomenon that you want to think about, an equal probability of occurring anywhere between 1 and 11 minutes from now. Just to get the basics out of the way, please remember that for this to be a probability distribution, its area has to equal 1. So already we can start doing some math on it. We know that its length is 10 units. And for it to have an area of 1, that obligates us to see that its height must be 1/10 of a unit. So that's a probability distribution. Its area is now 1. So good. Well, we can do some problems. Let's imagine that we have such a probability distribution, and we're asked, what's the probability of a randomly selected event occurring between, let's say, 2 minutes and 9 minutes. Okay. To do that, we're going to have to do that in terms of proportions. There's a few ways we can do that, but the first way that I want to talk to you about it is actually a little bit easier. It's not necessarily the most rigorous way to do this, but this is always going to be correct, and it's one way that's very easy. I know that the length of this is 10 units. Well, I can figure out the length of the interval that we're being questioned about, which is going to be the right endpoint minus the left endpoint. We're talking about these 2 points right here, 2 and 9. And we want to know how much of a proportion this is out of the whole. So I'm going to find out how long that is. I'm going to subtract 2 from 9, and I get 7. Well, we can answer the question, the probability that some randomly selected event will occur between 2 and 9, simply by taking that as a fraction out of the whole. I know that the length of the interval is 10. I know that this is 7. So our answer has got to be 7 units out of the total of 10. In statistics language, probability language, we would say that the sample space is 10 and that our desired event, the event that we're investigating, is 7. So I put the sample space on the bottom. I put the set of events that we're investigating on the top, and I get 7 out of 10. Now, you don't need to think about it in exactly those terms. You can just think about it as a proportion question, and that's just fine. Our answer is 7/10. There's another way to do it. You can do it by area. We just decided that the length of this interval that we're investigating is 7 units. Well, I know that the height is 1/10. I know that the area of this overall object, this construction, is 1 unit. So I can take the length of the interval that we're investigating, 7, and multiply it by the height of the interval. And that is a second way to come up with exactly the same answer. Let's try some others. Let's try the probability of x greater than 3. So now we're talking about a point somewhere around in here and then everything to the right. Well, I can assume that when it says x greater than 3, that it means x greater than 3 as far as the probability distribution goes. So that really means I have an interval length, and I'll just clean this up a little bit and redraw it to represent what we're doing for this problem. That means I have an interval that goes from 3 all the way to the end. So the length is going to be 11 minus 3 equaling 8. And that's 8 units out of the total available of 10. And that's my answer. Or alternatively, 8 times the height to do it by calculating area. And I get 8/10 that way also. Leave me a comment below if you have any questions, and I'll address them. I hope that was clear enough. We'll do one more. I'm going to make this a little bit more complicated. I want to know the probability that x is less than 3, or, that's the symbol for union, it can be read as or, x greater than 9. How do we solve something like that? Well, we're going to have to do it in 2 parts. We know by the addition rule of probability that we can just add these 2 probabilities together to get the overall answer for this problem. So I'm going to figure out the probability that x is less than 3. That means this area, and that would be 3 minus 1 equals 2 units, or 2/10. And I also want this zone, which is 11 minus 9, or also 2 units. So the proportion or probability represented by this part of the distribution is 2 out of the 10 units. And if we add those together, we get 2/10 plus 2/10, giving us our answer of 4/10. So that's part 3. Uniform probability distributions, at least to start out with, are pretty simple. You can really work with them pretty easily. And for part 4, we're going to be doing other types of distributions, also linear, but a little bit more difficult.